Hi, my name is Sammy, and today is all about efficiency. We're going to figure out how to build functional programs at scale, and most importantly, how to actually use functional programming in production. I already made a video introducing the basics of functional programming, so if you haven't seen that already, definitely do check it out. Link in the description below. Also, I apologize for taking so long to upload, but this video is an absolute banger, so I promise you it's worth the wait. Alright, so as you might remember, a function is called pure if it has no side effects and it does not reference any external state, i.e. it must always return the same output for every input. Suppose you're ready to make your next $1 billion and you read one article online saying that anyone can get rich quickly by making a social network. You're too dumb to use a database, so you store all of the tweets in a list and use a simple function to track the tweets on your server. In the mutable style, it might look like this, which is not pure because the function modifies its input to achieve the result. The update to all tweets is a side effect of the function and a side effect of me editing my slides in production. If we wanted to make this function pure, we'd have to copy the entire thing every time the function is called. This style is called a defensive copy, and it's a common pattern for turning mutable methods into functional ones. It doesn't take a Harvard dropout to understand the problems with this method. If we have to copy the entire list every time the function is called, our entire program is going to be very slow and use an exorbitant amount of RAM. We need some way to modify the list without copying everything around everywhere. In order to solve this problem, we turn to the first absolute powerhouse of functional programming: data sharing. Most programs rely heavily on arrays for fast random access to the elements. But to keep things simple, let's start out by talking about linked lists. We'll get to arrays though, don't worry. Alright, so let's start with a linked list and try adding elements to it. A linked list consists of a root node, the first element of the list, and then each node points to the next element of the list up until the last node, which points to nothing. We can implement a linked list with a pretty simple bit of code where each node, starting at the root, has a value and a pointer to the next element of the list. If I want to add an element to the back of the list, I can create a new node and then update the current last element to point to it. But if I want to add something to the front of the list, that's when the magic happens. Since the newly added node is now the root of the list, to add it to the front, I can just make a new node with some value and have it point to the rest of the list. What's crazy here is that we didn't have to modify any of the other elements in the list. None of these nodes changed. All of their values are still the same, and all of the arrows still point to exactly the same places. This is different from adding an element to the back of the list, because previously the last node in the list points to nothing, and we had to update element 4 to point to the new last element. Let's take a quick look at the code to add something to the front of a list. We create a new node to operate as our root, and then at the end of the function, we return that new node. What's going on here is that all tweets, the original list, is still its own linked list. And so what we're doing here is we're saying start at the newly created node, and then when you go to the next one, go through the elements of the original list. We're not changing any of the elements here, we're just changing the return value where we start the list. If we returned the second element of the list instead of the first one, it would look like the original all tweets unmodified. If all tweets is immutable, this effectively makes a copy of the original list with the new element added. We've achieved the same result as our defensive copy without using an exorbitant amount of memory. Going a step further, let's look at what happens when you call the function more than once, using the same initial list as input to both function calls. What's really cool here is both new lists point back to the original list. I created two new lists here, but they both share the same bits of memory, i.e. it uses even less memory than two mutable lists. This only works because all tweets is immutable. If it weren't, then any updates to all tweets would affect both lists. In this way, there's a little bit of a trade-off between mutable data structures and immutable ones. You're only able to share memory because the data structures are immutable. So you can get data sharing or modification, but not both. Alright, now it's time to turn up the heat a little. If you know anything about linked lists, you know there's a reason why nobody uses them. For most of the things you'd want to do, they have just abysmal performance. Linked lists boast an O-event hit if you want to do lookups, inserts, and even updates. In this regard, they get absolutely demolished by arrays, with array lists performing all of these operations in constant or amortized log n time. In order to solve this problem, we're going to need something big, something powerful. We're going to need trees. If you've done any basic computer science, you know that trees have log n performance for most common operations, including lookups, inserts, and updates. But what about immutable trees? How do you update an immutable tree? Let's start out with a very simple tree and a very simple implementation. We're not going to worry about sorting and balancing, but the principles we'll go over in this section apply to those more complex data structures. Alright, so let's say we have a tree and we want to modify one of its values. Just like before in our linked list example, we can create a new node with a new value and set its children to point to nodes of the existing tree. But as you might have noticed, there's a problem here. The parent node 3 was never modified, so it still points to the old node 6 in the previously existing tree. In order for this to work, we need to create a new node 3 and point it to our newly created subtree. What's really neat here is when we added node 10 as a child of node 3, we added the entire subtree. And similarly, when we set the right-hand side of node 3 to node 9, we set it to the entire subtree of node 9 and all of its children, unmodified, which means that we didn't have to make any changes to this entire subtree when we set it as a child of node 3. Since the element 3 is now changed, its parent now points to the wrong place. So we have to do this again so that the root element points to the new 3 instead of the old one. What's important here is that when we create our new node 1, we're passing in entire subtrees on either side. So when we're creating it, we give it our 3 subtree and our 2, 4, 5 subtree, completely unmodified. Let's zoom out for a second and see what we had to do to create a new tree with the element updated. We had to create a new node for the updated element, as well as new nodes for all of the ancestors of that element, going all the way up to the root. But what's really special here is we did not have to change anything else in the tree. All of the other branches here are completely unmodified and passed in as entire subtrees to the newly created nodes. In this way, the update performance is entirely dependent on the depth of the tree and not on the total number of nodes. For reasonably balanced trees, this gives us log-n performance for updates alongside inserts and deletes by following the same principles. We can choose to update elements in a way that respects sorting, and we can also use these immutable update principles to perform the operations that rebalance the tree. Using these immutable trees, you get access to all the operations you need in log-n time, because hash maps and sets can be implemented using arrays. We also get access to immutable hash maps and immutable sets, all with log-n performance. This gets you an immutable version of basically any data structure that you might need. This also means that the same algorithms that you're used to using in the mutable world still work in functional programming. You can just use immutable maps in the same way that you would use arrays, although you'll need some sort of recursion or a reduce to loop through the elements. You'll still need an O of log-n hit to performance, but in practice I've found that Clojure's immutable data structures are good enough to handle real-world applications. Alright, so we figured out how to implement functional programs that run efficiently, but that still isn't enough to use it in the real world. That's because in the real world, things are messy, and the real world is mutable, so we need to figure out how to get our programs to model this messy behavior. Today we're going to go over 2 of the most common production applications and see how we can build them in a functional style, building a website and building a UI-driven client-side application. As you might remember, a web server is just a program that listens for requests and then responds with the content of the web page. This is actually really similar to the setup of a function, which takes an input and returns an output. We can answer web requests by building up a response template consisting of smaller subcomponents. And there's a detailed explanation of how to do this in the previous functional programming video. But here's the thing, real-world servers aren't that simple. In the real world, servers need to interact with other stuff, and they often depend on some external state in order to work correctly, violating one of the very principles of functional programming. When you visit a website, you don't just want some static web page. You want to know what time it is, or what is the weather like in Chicago. You might even need to check some ever-changing credentials in order to verify that a user is logged in. When you make a request to a web server, it usually makes another request to another web server or to a database to actually get the information. If we wanted to make this pure, one way we could handle it is to just make all of the database calls and do all of the external requests at the start of evaluation, and then just pass it in as input to the function that builds the response string. So when your web server gets a request, it immediately makes all of its backend calls to the database and other external servers. It passes it as input to the response function, which then returns the response. If I also wanted my request to have some side effect on the outside world, in addition to the HTML response, like posting a tweet or updating a database, I could achieve this by having my pure function return an additional piece of information describing what changes to make to the outside world. In this way, our web server has side effects and depends on external state, but these are isolated to the beginning and end of evaluation. The bulk of our program, where all of the logic lies, is still pure, and so we can still use the principles of functional programming to implement the majority of our web server. This simple organization is actually enough to work for many production apps, but occasionally the various sources of input and output have interactions with each other that make this even harder to manage. Luckily, this isn't even necessary for many production websites, but for the ones that are, we have a few strategies to deal with this. The easiest, and probably the most common way to handle this, is to just think of the operation as several different sub-requests, where each request has its own additional input and output. Another interesting strategy is to use lazy evaluation to treat all of the sub-requests as input created at the start of the program, but then only access the ones that you actually use to avoid creating a million unnecessary database calls. In general, this strategy of tacking input and output to before and after calling a pure function is a really common pattern, and it's actually really similar to what super pure languages like Haskell use to model side effects. In practice, most production servers, even ones that rely on the principles of functional programming, use a little bit of a mix of both, with large blocks of pure function and immutable interactions isolated to a small section of your codebase. It's what I used for my own website, a customizable newsfeed, and it's a common way of thinking even for developers who aren't super into this functional paradigm. As promised, we're also going to talk a little bit about UI-driven applications. Most games and many UI-driven applications use the model view controller architecture. Basically what this means is that internally, the game has a model of the world containing things like the position of Mario and the position of all the enemies, and it uses that model of the world to render what you actually see on screen. And the user, or the player, presses buttons that actually update the model of the world. Usually for many games, the way that this works is there's a certain frame rate to the game, say 30 frames per second, and on every frame of the game, it gets the next user input and the next time step and uses that to generate a new model of the world. And then it uses that new model of the world to actually re-render what you see on screen. It loops that process frame by frame, sort of like playing a movie. What's really neat about this is that the side effects and the inputs of external state only happen at the beginning and end of these operations. We take input from the user and use it to produce changes to the model, but the process that takes that input and decides what changes to make can itself be a pure function. Likewise, when we render the view, we accept the external state, the model of the world, as input, and we produce all of the side effects, what you actually see on screen, as output. In this way, we've broken our program into two pure functions, separated out by mutability and global state. Now, so far, we've only shown how functional programming can catch up to the mutable style. But in order for it to actually, be useful and worth the effort, we need some ways that it's even better than mutable programming. Some of the biggest benefits of functional programming are that structurally it's simple. All of the advantages discussed in the previous video still apply here, which means that functional programs can be easier to test, have a smaller API surface, and have fewer sharp edges when working with concurrency. I'm not going to re-explain those here, but definitely do check out that video for a more detailed explanation. These things are all super important for production servers because you want your production applications to be reliable and maintainable. In this video, we're going to go a step further and introduce a few more concepts that really set functional programming apart from its mutable counterparts. It's time to introduce the second major powerhouse of functional programming: memoization. See, pure functions are really special because they behave less like a procedure and more like a function in mathematics. Because a pure function has no side effects and it always returns the same output for every input, the behavior of the function depends only on the mapping of inputs to outputs. And in particular, it does not matter how the function is executed, as long as the mapping of inputs to outputs is the same. What this means is if we know the mapping of inputs to outputs, we don't even have to execute the function. Let's take a look at a simple example. The first time I call this function, it does some complicated calculation in order to produce the answer. But the second time I run this calculation, I can just remember that every time you input 12, the answer is always 13. And because the function is pure, this answer never changes. And we don't even need to run our something complicated because it has no impact on the outside world. So if we just store the mapping of inputs to outputs in a hash map somewhere, instead of recalculating the answer every time the function is called, we can just return the value stored in our hash map. This is one form of caching, and it's special because when functions are pure, we can always cache the result without impacting the behavior of the program. Technically, updating a cache is a mutable operation, but because it doesn't impact behavior, we can work with it like a compiler optimization rather than a true side effect. You do still need to be careful though updating a cache in a multi-threaded environment. This is super important for web servers because the web server needs to respond very quickly to requests, even though it might be doing much more complicated computation behind the scenes. You might be wondering, since do something complicated was never used, why do we even need to call it at all? Another very important benefit to this referential transparency is the ability to do lazy evaluation. Basically what this means is because function evaluation has no side effects and always returns the same answer no matter when you call it, you don't actually have to evaluate the function when the function is first called. You only need to evaluate it when somebody actually goes to look at the answer. This might not seem like a big deal, choosing to evaluate something later rather than now. But in practice, programs request the answer to things that they never use. It'd be like if you went online and you ordered a burrito. When you first put in the order, the burrito company sees that you ordered a burrito but doesn't actually do anything. It's only when you get to the store and you say, "Hey man, where's my burrito? I'd like to start eating it now," that the store says, okay, I'll start making the burrito. On average, it saves the store time and money because a lot of people put in orders that they never decide to pick up. I personally don't rely too heavily on lazy evaluation for my own programs because while it technically improves performance in the average case, I find that it makes my production applications harder to profile and understand. If something suddenly takes 10 minutes on the CPU, I need to know what kicked off that process and why it's running that way. And it's often hard to understand the chain of dependencies that caused some distant part of the program to need that value. Last up, I want to talk about something that isn't specific to functional programs, but usually improves performance as a result of the way that functional programs are often designed. Typically, when you make a for loop in Java, way back in the days before for each loops were popular, it would look something like this, where you would loop through an array by iterating over an index. In contrast, in the functional style, it would look more like this, where the operation to do something to each index is accepted as a function as input. It's subtle, but the functional style is a higher level description of what you're actually doing. Both of these implementations tell you to do something to each element of a list, but the imperative style describes how to do it, whereas the functional style just tells you to do something to each element, and it leaves the implementation up to the compiler, or the language. These higher level operations give the compiler and the language more flexibility to do optimizations under the hood that improve the performance of these operations. In a nutshell, functional programming is more restrictive, but as a result, you get access to stronger invariants about your software that make it easier to reason about and to optimize. Thanks so much for watching. If you enjoyed this video, make sure to give it a like, subscribe to the channel, and I'll see you in the next one. Also, for my next video, I was thinking of doing a Guess the ELO style video where you all can send me code, software, projects that you've written, and I'll give you a real code review and then try to guess what level of experience you are. Either a novice, a student, a junior, or a senior developer. If you'd like me to look at your code and talk about it on the channel, leave a link to a public GitHub repository that you are the author of, or a pull request that you've made. And if we get enough submissions, I will pick out a few to review on this channel. Again, please link your own software in a public GitHub repository that does not contain any private or confidential information. Again, thanks so much for watching, and I'll see you in the next one.